Hello everyone, welcome back to our video tutorial series and lectures of just using Grasshopper to create architectural models that we can use in our projects. So as you know, we've been sort of looking at how to create models similar to this, and we've focused on the surface by itself, but what we're going to do in this video is we're going to focus on how to extract the underlying grid shell structure. And a grid shell structure is a structure that's composed of linear elements that connect a series of nodes. And surfaces like this that have double curvature are very firm, are very stiff. As you can see, this has a considerable area that it can cover, but it's a really good way of covering large spaces. And this in particular is a work by Paulina Sierra, a former student of mine who created this model. So let's see how to do it in Grasshopper. So I'm going to start showing you my screen. And here is the final model that we're going to be looking at today. As you can see, we have these elements. Each one of these is notched. It has a notch. And the notch width W, let's call it notch width, will be equal to the material thickness. Oh, thickness. Oh, sorry. Well, yeah, let's write it down properly. So let's do that. Let's do the notch width, which is this distance right here, will equal the material thickness. In this case, in the case of this model, we're using MDF, which is 2.5 millimeters, or sometimes it can be 3. You can measure it using different instruments, but anyways, that's kind of, you can also have 3 millimeter thickness thick. So there it is. So let's look at how to do that. Let's create that, and we're gonna do yeah, let's just, well, another thing is that you have elements that are flat on one direction, and you will have elements that are flat on the other direction. And as you can see, one layer of the grid shell will have the one layer of the grid shell will have the notch pointing downwards, and the other layer of the grid shell will have the notch pointing upwards. So that's important so as to create this assembly or this connection between the two pieces, so that then when they work together, they will work together as a grid shell structure. And what a grid shell structure is, a grid shell structure is a structure that is very firm, is very stiff. It has a lot of stiffness because it has double curvature. So anyways, that's kind of the reason that we're doing this. So let's get to it. So what I'm doing is that I'm starting from, we have a surface like the one we've been using for a while from previous videos. And what we're doing is that we'll start with the surface, and we did the panelization. We have indeed the panelization here. We're not going to use these panels right now, but we are going to use the same U count and V count as our surface panels, because we have like our surface panels. So we're going to use the U count and V count from those to create a corresponding structure underneath these panels. So let me just show you, if I show you, you can see that we have the same division. Actually, that line that connects two panels, it's exactly the line that connects the intersection between the two gridshell layers, or the gridshell structure sets. So anyways, that's important. We're going to use these same divisions, and I'm going to go to surface, utilities, divide surface, and I'm going to plug in the original surface, and I'm going to get the same U count and V count. Oh, sorry, the same U count and V count, and that'll give me a tree of points. And as you can see, this is already a tree like we've been working with. It has 16 branches with 29 elements, and this one should have 15. So it looks like yeah, it's fine. It has one more count, one more structure count than the panels, because yeah, the panels, they're the strips, and these are the perimeter as well. So what we're going to do is we're going to create a curve, a polyline that connects all of these points. And as you can see, they are arranged on the U direction. As you can see, we have 15 polylines, 16 polylines. And we also want the other 29 polylines on the other direction. So we want to have these polylines, which are going to be 16, and we want these polylines, which are going to be 29. And to do that, we need to work with the tree that comes out of this component. And we're going to flip, if we have a tree, let me just explain this. If we have a tree that has 16 lists, each one of those, yeah, it's like 4 by 4, yeah? So it has 16 lists, and each one of those lists has 29 points inside of them. That's what we have. That's what's coming out of this, because it's telling me that 16 branches with 29 each branch. So what we have is 29 points here, 29 points here, 29, etc., all the way to the last one. Yeah, so each one of these has 29 points. So we're gonna turn this tree into something else. We're gonna turn it into a tree. Oh, sorry. We're gonna turn it into a tree that has, it's gonna have 29, but each one of those is gonna have 16 elements inside of them. So let's just, you're gonna have, it's the same tree, the same data, but we're gonna create new lists inside of it with the same data, the same, this is gonna be a tree with 16 branches. Each one will have 29 items, and this one is gonna have 29 branches with 16 items each one. So that's what we're gonna do, and to do that we're gonna use flip matrix command. And that's what we're gonna do. That's gonna be on sets, tree, flip matrix. There it is, flip matrix. So yeah, let's do that. Tree, flip matrix. And now that's flipped, you can see that now we have 29 branches with 16 elements. So it's, and we're gonna copy the polyline component, And now we have both sets of polylines. We have 16 polylines on one direction and 29 polylines on the other direction. What we're gonna do now is we're gonna go to Surface, Freeform, Extrude, and we're gonna extrude these, each one of them, well, both of them. Let's do it 2 times. We're gonna extrude them on the Z direction. We're gonna go -3. We're gonna go -3 on the factor to get that. Yeah, let me just hide everything. And we're getting these and these, as you can see there. I think -3, it's a little bit too much. Maybe I want to go -2. There we go. Just a lighter version of that. So right now, this distance from here to here, it's -2 units, right? So anyways, what we're gonna do now is we're gonna get this point. We have this point. We're gonna get the midpoint of those 2 points. We have this points, and we're gonna get these. And using those, we're gonna create a cylinder that will go up, and then a cylinder that will go down. And they're gonna have their center at that point, so they're gonna be concentric. Both cylinders are gonna be concentric. So yeah. So we're gonna create concentric cylinders using that midpoint right there. So what we have to do is we just have to get the points. We just have to get these points and move them down 1 unit. So let's go to transform, Euclidean move. We're moving these points, vector, unit Z, -1. So there we go. And there we have those points there. Right now, these points are arranged in a 16 branch tree. As you can see here, that's a 16 branch tree, and that corresponds to this. If we do that same thing, we can copy that, or we can just copy the move. Oh, sorry, I think I copied it. If we copy the move and we do that with the matrix, we get the same points, but we get the other tree. So let's do that for both of them, and let's just have them just arranged with our ribs, with our grid shell structure. And now that we have these, let's just say that this is the U direction, and the U is gonna have the notch pointing upwards. So let's go to Surface, Primitive, Cylinder. And the base of the cylinder is gonna be this. And the length of the cylinder is gonna be, I don't know, it can be a large number like 20, for example. So they're tall cylinders. And the radius, let's just do 0.15 for a 3 millimeter. For a 3 millimeter MDF, let's do 0.3. This is in centimeters, so that's pretty good. And now we're gonna go also to Surface, Utilities, Cap. We wanna cap the holes of the cylinder. Right now the cylinders are open, and the caps are these ones. So that's the cap right there. And we're gonna do the same, but with these points over here that are arranged on the other data structure, and the length is gonna be -20. These cylinders are gonna have their notches, or they're gonna cut notches pointing downwards on these ribs, and these cylinders are gonna point the notches upwards. And as you can see, we have the same data structure on these two. So this is the upward pointing notches, and we have the same data structure on these two, and that's the downward pointing notches. So what we're gonna do is we're gonna go to, I think it's intersect, shape, trim solid. It can be trim solid, or it can be, yeah, let me just check it real quick. It's solid union, no, it's yeah, trim solid, perfect, trim solid. So we're gonna use trim solid. We're gonna, the extrusion is the shape, the ribs are the shape, and the cutters are the B-ribs, the cylinders. So this will give us, this one takes a little while, but it's pretty good. It's giving us the notched surface. And we're gonna do that with the next one, shape and cutters. Takes a little while, but it'll do it eventually. And now we have these two guys over here, right? Okay, so I'm gonna hide everything else. And as you can see, we have now our structure, and these surfaces, these are single surfaces, but they represent the shape of the extruded or of the solid that's there. In reality, what we can do is we can just bake these. We can bake one set into a layer, and we can bake the other set into another layer. And we can now, if we were in Rhino, we can work with this, and we have both layers, or both directions of the surface, and we can now do unroll surface in Rhino, as I showed in the previous video. Oh, sorry, it's breaking it up. It's breaking it up. So maybe we're gonna unroll, but without exploding. Yeah, there we go. Yeah, so that's pretty good, and we can do that for each one. But as we saw in the previous video, we're gonna use the unroll command of the we're gonna use the unroll command. We have to flatten this. We have to flatten it. Yeah. And I think they're all the same, actually. They're all the same, yeah. They're all kind of the same. Yeah, they're all pretty much the same curve. Because it's a translation curve, they're all going to be the same, right? But we can now use OpenNest to do the same thing we did. We can set up our rectangle that goes from 0 to 90, and then it goes from 0 to 60. Remember, this was in centimeters. Now we can plug that into sheets. We can plug that into, we can go with the curves, actually. We can go with the curves. Oh, sorry, this needs to be flattened. Yeah, flatten. And there we go. We have now, we should have, it's, what's going on? Is it doing it? Let's try the B-reps. So yeah, I just used the OpenNest command. It looks like it took a little while. You can change the tolerance, rotations, and the iterations, for example, but it takes a while. Right now it just has one iteration, but if you have time and your computer can take it, you can change the iterations to 10 or something, and it'll optimize this and maybe put them all into just one single one. And you can check last videos. You can check the other videos where we saw how to tag these. And but anyways, that's how to create the substructure for the model. So again, you can just bake these or get the borders, get the B-rep edges and just export that into the laser cutter to create your model. So good luck with that, and I'll see you on the next one.